Hey everyone, welcome back to the Curlyboi Theatre. Right now, I'm very excited to introduce Peter Vanderburg, who's going to be talking about the art of MicroPython. How are you doing today, Peter?
Oh, very well, thanks, Lily. Yes, excited to be here.
Excited to have you.
Thank you.
Now, just as a quick bio to introduce Peter, Peter's career spans a few decades in telecommunications and local government as a technical specialist, and then into management. Now he's contract IT project manager and a freelance Python programmer in Melbourne. Peter likes to tinker with electronics and interfacing microcontrollers with the real world, mainly MicroPython, and upcycle obsolete computer hardware into both jewelry and art. So really excited to hear you talk about MicroPython and art. And I'll hand it over to you.
Thanks very much, Lily. And welcome everybody for joining me this afternoon. It's great to be here. Excuse me. So the art of MicroPython. This piece was created for an exhibition in my local city of Whittlesea here in North Melbourne last year. And I was quite chuffed to actually get an award. So yes, we've just heard a bit of a bio, but I like to create mixed media art, and there's a few examples there. But I also like to take the opportunity right now to thank Effie, my partner, and the family at home for their support and encouragement. That motivates me to create such materials, as well as my mates at the meetup, Matt and crew, and also the support of local artists here in the city of Whittlesea. So this is the artist description, the artist statement that goes with the piece. You can see in the photo that it's reasonably large, 600 by 600, and that gives a bit of scale to the piece. So the synopsis today really is to give a bit of context for the code. We need to understand the mechanical and electronic aspects of the creation to really show what I was trying to achieve. We'll be looking into the code in detail that synchronises the electromechanical aspects and how I overcome the few challenges that I had in making it all work. It's always useful, maybe you have this yourself, that when you embark on something, is have a few principles that guide you along the way. Clearly, as being an artist, I begin with the end in mind. I have a very clear vision of what I want. But these principles really help me to remain focused. Pareto is clearly my number one, where I find that generally 20% of your effort gets you 80% there, and it only takes a few iterations to get you about 99% there. When I'm coding, always have a fully working system after an editing session. If not, roll back. I've got to keep telling myself that it'll never be perfect. Perfection is a bit of a perfectionist. Perfection is subjective. And point number 4 is important as well, is it's only a problem if it's a problem, otherwise stay away from it. And of course, it can always be improved. But remember points 1 to 4. So why MicroPython? Well, back in the early 80s, I got my first computer. It was a ZX81, and with that, I started tinkering with assembler, basic, Forth. And then later in my career, I became a Unix systems administrator, where I had to focus on shell scripting, Perl, and SQL. And I managed to steer well clear of C. And then about 5 years ago, I decided to get back into hardware. Of course, the microprocessor world had changed a bit since the 80s. And with Raspberry Pis, and I bought some Arduino hardware, got back into it. Now, what I found with the Raspberry Pi, I could program it in Python. I hadn't actually come across Python. Well, I'd come across it, but I hadn't lifted a lid on it. So with Python, I found it was very easy to code and get results quickly. Not so with Arduino. I found Arduino too much C-like, and I went, nah, this isn't for me. But while I was researching Python and Raspberry Pi, I stumbled across a talk that Damien George did here at PyCon a number of years ago on the merits of Python for hardware, MicroPython, and I dug into that, and I was hooked. Got rid of the Arduino stuff and the working on the ESPs. And so for this application, MicroPython was the no-brainer. So contextually, the mechanical construction. So the whole frame is 600 by 600. I used a PC motherboard PCB as Fibonacci forms. So there are 4 of those. They're connected through an axle to a gear on the other side, 3D printed. That's connected to a hobby servo, and so that's the mechanical part of it done. And for the lighting that I've got around the edges, I used acrylic rod as a diffuser. For the electronics, there are lots of neopixels. They're about 70 all up across the whole creation. A couple of ESP 8266s and switch mode power supplies. And this is what version 1 looked like. So here we've got one ESP 8266 using, it's a simplified diagram, 2 GPIOs, one for the pulse width modulation to the servo, there's a direct connect, and another line to the neopixels for the serial data stream. I needed 3.3 volts and 5 volts, and that was fine. Very, very simple. And the code for that was equally simple. So you know, just keep things straightforward. Have an open sequence and a closed sequence, pretty much the same. And here I've got a start position, a stop position. Send the position to the servo, and that same number is a lookup for a LED function that then kicks off the appropriate animation. But it was inherently unstable, so unstable that it was damaging the hardware. So I found that the LED dimming sequences seem to affect the pulse width modulation timing, and those changes in the timing get amplified in the servo, and the servo was basically shaking the structure to pieces. The small DC motor, while it was concentrating its power into a very small angle, there's a lot of torque in behind that. And these servos are very fast acting, and with the mass connected to the whole structure, there was too much force for the little motor, and I burnt out the motor. In fact, I went through a few servos solving the problems. So the first set of solutions was to separate the LED functions from the servo. So the electronics, we're talking about the hardware. So the LEDs were connected to one microcontroller, while the servo was connected to another. And I also boosted the power. So while the voltages were fine, the instantaneous current demand from especially the servo and the LEDs was too high for the original power pack. And so with a laptop power supply with lots of power, truckloads of power, and a couple of high efficiency buck converters, I managed to solve that problem. But that created a new problem. How do I synchronize two controllers? I looked at I2C. However, in the ESP, the I2C, these devices can only be masters, whereas I needed a master and a slave. I didn't have a great working knowledge of SPI, so SPI could have done it, but I didn't have the time to dig into that and get that working. So I chose a simple method of using some GPIO lines, 3 of them. So the master is the outputs and driving some inputs into the second controller, and that's what that looks like. So on the top left there, we have a counter reset, the step pulse, and the direction flag. So it's just 3 lines across. So looking at the code, once again, the close function, I added a bit of extra stuff into here. And I added a function that this function here, external servo, that handles the pulsing from the master to the slave. On the slave, we have the inputs, the 3 inputs. So we get the step pulse, the direction flag, and the counter reset trigger. The trigger is to ensure that the counters remain in sync between the two devices. And the code for that is when initializing the second microprocessor, we're setting the pins as inputs and instantiating the interrupt callbacks with functions as the interrupt handlers. So basically, the slave just starts up with the pins, and then once the interrupts have been instantiated, it just sits and waits for interrupts. But it was soul destroying. Going into the gallery, it was soul destroying, seeing my precious dying. What was happening was that I'd overlooked one aspect of it, which was that the gallery staff didn't know how this thing worked. And I'd made a big assumption that it'll switch off in the closed position, even though at that point I hadn't explicitly programmed it to do so. The staff would switch the unit off at the end of the day and switch it on in the morning. And if it wasn't in the home position, the initialization of the servo would literally whip the forms into the home position and then attempt to start the routine. And as we saw earlier, that created there's a lot of energy in that, and it was destroying the motors, basically. So now it is a problem. I need to do something about that. But before we can solve that problem, we need an anatomy lesson of a servo. So a servo is quite a complex little beast. We've got an ordinary DC motor that instead of having just voltage across the motor, has control electronics. The output of the motor, the shaft, drives a gearbox, which gears it right down, and attached to the gearbox is a potentiometer, and it's the knob essentially of the potentiometer is connected to the gearbox, and then that creates a feedback loop back into the H-bridge electronics, which compares what the signal is, that compares the pulse width with the feedback in the electronics, which then determines the voltage that needs to go across the motor. So when things are equal, there's 0 volts across the motor and the motor is stationary. If we change the duty cycle here, then we get a voltage which drives the motor, which drives the gear, which drives the shaft of the potentiometer, which creates an error. and then corrects it. So this feedback loop, it's closed at the moment, but we need to open that up and we need to put that into our processor and use it. So that's exactly what I've done. This is one of my broken servos. So it's just a Tower Pro hobby servo. So we've got the motor there, we've got the gearbox there, and this is the electronics, the H-bridge electronics here with the standard 3 wires, pulse width modulation input, plus up to max 7 volts ground. And then I attach this blue wire, or in this case a blue wire, to the wiper of the potentiometer, and that gives me a 0 to 3.3 volts, which is very convenient. So attaching it to the hardware, so 0 to 3.3, the ADC and the ESPs has a dynamic range of 0 to 1 volt and a count of 0 to 1024. So what I do here is through a very simple resistive voltage divider. So while I get 0 to 3.3 volts there, I get 0 to 1 volt there. And I feed that into both microcontrollers, so both the master and the slave can keep track at all times of where the servo is. So what do I do with it and how do I use it? So I could simply just create a table of duty cycle versus ADC voltage, but when I was working on that, I found that I was getting differences between the hardware. And of course, we're dealing with analog electronics here. So, and not all analog devices are created equal. And nor are all ESPs created equal, as I also found out. So I was having different results of different combinations of servos and ESPs. So I needed to do something else. So to determine the linearity of these devices, I created a small bit of code, very simple. So I've got the range of the duty cycle, and I just read the voltage, and I put it into a list or also a CSV. And with that, I do a linear regression analysis. Now, Microsoft Excel conveniently gives that in the form of a scatter graph, which is the pragmatic approach that I took. And I did subsequently find a Python way of doing it, which I'll show you. But the pragmatic approach gave me this. And so it's nice and linear, it looks nice and linear, but if you look closely, you can see it's a bit lumpy. You can see a few dips, a few rises, and here's one here. And what when we're traveling through the duty cycle, it's at that point there, it would actually shudder. The servo jumps and up here as well. But it was linear enough for me to get this formula, which is exactly what I needed. And just for fun, we can do it in Python. Now, Python, CPython, and there's some very good libraries out there. I understand that NumPy has methods for regression analysis, but I wasn't going to go into that. So this is a longhand way of achieving the same. This website here gave me a trend line, and then I just converted that into some longhand, and this was the result I got, which was very close to the Excel method. So I was happy with that. And so this is how I use it inside the slave and the master. The same function. So for every voltage, I get a position, and then I do a comparison of what the code thinks the servo should be positioned. And on the master, as a problem that I did have was that the thing could stall, but as I also found out that it doesn't necessarily work that well because it's a low-powered too much current in the motor for too long will burn it out. And if I was jamming it up, that could be 5 seconds, and it doesn't react fast enough. But this is basically we're reading in the ADC. We step the servo. We read the ADC again, and if it shifted, that's great. So that's where we get the new position. And if it has shifted, all good. If the difference is too much, then we've got an issue. On the slave, however, this is more critical. The startup is where it comes into its own. So if it was when the unit is switched on and hasn't come home, it's the slave is looking to see where it actually is, and so the master is also monitoring the ADC and will not start the main routines until it is home. So the way that we do that is, so we've started up the slave here, and it's just waiting for the interrupts to be activated. But before I do that, we will reset the master. Reset the forms to make sure they are home. And this is it here. So just a little step routine, and essentially it's like what we're seeing before. Reads the voltage, sees what the position should be, and if it's not at the start, then call the stepping routine until it does reach home. And when it does reach home, then we can start up. And with that, let's see how it looks. So here, pretend that it's the end of the day. Oh, it's been switched off. The gallery attendant goes home, comes back in the morning, switches it on, and now it's homing, and it'll keep slowly stepping back into home until the master detects that it's home. It'll stop flashing. There we have it, and now it starts up. And that, my friends, is the end of my talk. Very happy with the way that MicroPython can be used in something as abstract as this. Very, very fast to prototype with. Overall, I used about 15% of my time on the actual coding, leaving 85, that old Pareto 80-20 thing. Most of my time went into the visual aspects, which is what I really wanted. So thank you for attending, and thanks very much to the PyCon team for this conference and for the opportunity to talk to you.
Thank you so much, Chris. I can see there's some applause drifting up there in the chat, so that's great. There's been some interesting discussion going on as well, but I know that speaking live, you won't have had a chance to see that yet,
No.
but you will soon. So we have people scouting for questions as they come through. But just to kick us off, because we do have a few minutes for questions, I'm interested to know more about what your next art project is going to be. Now that you've got this one out of the way.
Yes, there's another one that. In fact, I just don't have the time for it this year, unfortunately. In a month's time, my city has another exhibition, and I like using PCBs and the engineering, displaying the engineering that's gone into PC hardware. It's been created originally by people, so I consider PCB as a form of art in itself, and it's my way of preserving it. So in everything that I build, I like to have something from the electronics world sort of embedded in. And for the next one, I do have something in mind, but it's quite hard for me to describe it. I'm quite reasonably visual, and to articulate and to recreate that in somebody else's mind is quite challenging. I'll just turn that off.
Yeah, no problem. It's all right.
Yeah.
It's good. We're on time. Okay. So we have another question coming through. Is the feedback to the ADC dependent on the servo voltage?
Yeah. You got to put it through. You got to put it through a voltage divider. So it depends really on the microcontroller, the ADC range. With the ESP8266, it's 0 to 1 volt. Other microprocessors may have it up to the working voltage of the microprocessor, say 3.3 or 5. So in that case, if the servo was a 3.3 and you're going into an Arduino that has a 0 to 5 volt, you can do one of two things. You could actually amplify, so you get the 0 to 3.3 becomes 0 to 5, or you just feed it straight in as 0 to 3.3 and adjust your code accordingly.
Right.
But you just need to, in my case, I needed to know the dynamic range of what I wanted to work with and just work it accordingly.
Great. Okay, this question's starting to flow in now. Someone else would like to know, have you used CircuitPython?
No, I haven't. But hats off to Adafruit, though. CircuitPython is a fork of MicroPython, and what they did with MicroPython is to make it really easy for real beginners. I mean, MicroPython has a slightly steeper, I think, a steeper learning curve than CircuitPython, mainly because the assumptions you might have if you're brand new into it kind of work with CircuitPython, but not necessarily with MicroPython. For example, from what I understand at least, being able to access files and formats and SD cards and things like that, USB. But I haven't worked with CircuitPython, and neither do I necessarily want to. But there's a lot of cross-pollination across the two. So libraries or modules built for CircuitPython can be used in MicroPython with a little bit of tweaking, from what I understand. For example, the NeoPixel library was from Adafruit and is used in CircuitPython.
Thank you so much. I think that might be all questions that we have time for at the moment. But if you are hanging around after this, where can people find you?
Oh, where do you want me to go? In the Venulus thing?
Yes, in Venulus, there's a text chat. We have the Curlyboi Theatre hallway.
Let's go there.
Where the conversation can continue. Yeah. Okay, excellent, because there has been some great conversation there. Thanks. You.
Thank you.
Okay, we're going to take a short break now, just in the theatre, until our next talk, which I'm very much looking forward to seeing. So take about 10 minutes of break and we'll be back.